from the NFV, SDN, and network management research groups. We wanted to gather today and try to explore a bit some new orientation, research challenges, gaps that can happen in the management of virtualized and programmable networks. So I will be a bit sharing the session together with Diego Lopez and Koei Shiomoto, but we have also the other chairs from the research group that have been participating in organizing this event. So as you know, the IETF is following the same policy as IETF, so please be aware of the not well. So just before we start, I'd like first to start with thanking, we have already 2 minute takers and two scribes, one for the Jabber and one from the Meet Echo. So thank you to Aomian, Katalin. Katalin is in the room. Okay. And we have also Will and Dan, which accepted to be also Jabber scribe. Thank you for volunteering. You can also participate with the different Meet Echo and Jabber. The links are provided here, and we will also have the mailing list with some reports. So just to give a very brief introduction to the topic, the goal of the meeting is to investigate different problems or challenges that may arise for the management of virtualized and programmable networks, so in the scope of SDN and NFV. And we want to be able to develop a bit of a cross-research group, a bit more comprehensive understanding of the different interactions in these different technologies, and not to be always confined in the different groups or the different views that we may have. And so try to develop a bit of a more insightful view of what could be the next things to do from an IETF perspective, but also from maybe an IETF perspective in terms of standardization. So today, we are really interested in that the speaker provide their views on novel approaches or applicability of existing techniques and go a bit beyond the state of the art. So the two things, techniques and tools for the management and operation of NFV and SDN networks, but also the reverse aspect, which is how we can use virtualization and programmability to a bit renew the way of doing management and operating the networks. So we have a quite full agenda today. We have 10 presentations. Our recommendation is that, I will not go through that today because right now you will see this very soon, but our recommendation to the speakers is try to be as brief as possible, highlighting the main point of your research, of your presentation, because we will try to save time to have also interaction at the mic, interaction with the room. So if you can have 1, 2, or more questions at the end of your talk, I think it will be also help the discussion of this meeting. We try to provision at the end of the agenda also a bit of time for the discussion, but it was a bit difficult to put everything in the agenda. So if everything needs to be discussed further, we try also to continue on the mailing list. So this is what I highlighted just before, and I think I'm done. Any comment before we start or views from the audience? If not, propose that the first speaker comes to the mic and we will start the session. Thank you.
Morning, everyone. My name is Gurong from China Mobile, and I'm glad to be here to start with. I'm glad to be the first one to start with the special session, and my topic is about the consideration about the SDN network management. Yeah.
To find
maybe firstly, I can introduce about our network based on SDN technology. For several years, we have been trying to bring in the SDN technology into our cloud data centers. And up to now, we have several cloud data centers which are based on the OpenStack kilo version. the KVM hypervisor, and we use the vendor's controller and their forwarding nodes. And also we have our self-developed controller based on the ODL and our open source OS, but they are only with the status of small size, small try. And next step, after the newly built cloud data center, we come to the consideration about how to manage this work and this network. And we have found out that there are several changes comparing with the traditional network. The first is about the network levels. Now there are several levels in the network, such as the overlay, underlay. And when we considered about the tenants, the network can be divided into several levels from the top to down. The first is the service level, which is also called the application level network, which facing directly to the tenants. And in the middle, it's the logical layer, which is corresponding with the overlay network. And the bottom is the physical layer, which corresponds to the underlay network. And as there are many levels now in the network, so the information for the management of each level should be collected, which can be large scale. And besides, the fault of each level should be precisely located. And besides, the topology of each level should be displayed. And besides, one of the advantages of SDN technology is about the auto configuration. Then how about the auto management of the network? As there are many new encapsulation technology now in the network, such as the VXLAN, NSH, how about their OM? This is also coming to our consideration. Next, I will go to the details about the considerations. One is about the architecture. And we think that the management platform should be deployed in the top of the application layer for the use of the management information collection and the network visualization. And we divide the management platform into two parts. One is the tenants management, and another is the administrator network management. The tenant management is responsible for the tenants network, such as the application layer network, and the administrator management takes the responsibility for the overall control of the network. As we use the OpenStack in our network, as discussed before, so we firstly search for some open source OpenStack project which is related with the management. One is the HEAT and another is the telemetry. And HEAT is responsible for the orchestration, and the telemetry is responsible for the metering, monitoring, and alarming. However, due to our survey, we have found that the telemetry has not well supported by the vendors. So, or in other words, we think that it may be not very natural to use now. So we come to now consideration. How about some similar mechanism which acts as the telemetry in network management? The next is about the information collection. As the management platform is used for the management information collection, now the requirement of the platform is extensible, standard, and with high performance. About the extensible, as we know now, the network is with large scale, so it should be extensible. And the standard, the management information and technology are not very well defined or formatted, especially in the application layer and the logical layer. So we think that it should be standard and with high performance, as the information is with large scale, so it should be with high performance. The next is about the topology. As there are several levels now in the network, so we think that the topology of each level should be displayed dynamically. Such as from the tenant side, its application network should be viewed in the application topology. The tenants can see their own, such as the VPC virtual private cloud from their side. And from the administrator side, they can see their logical network topology and the physical network topology. And the logical network topology with the path of the VTAP to VTAP or the VTAP to the SDN gateway. And the physical network with the path between some physical devices such as the leaf switches. And now come to our consideration as the physical topology can be realized by some traditional mechanism. How about the application layer and the logical layer? Next is about the network monitoring. As well, there are several levels now in the network, so each level should be monitored. Each level of the network should be monitored, such as the tenant level, the application network, and the administrator level, the logical and the physical network. And also the physical network can be monitored by traditional mechanism. How about the application network and the logical network? The next is about the end-to-end detection and the precise fault location. Also, there are many levels of the detection now in the network. From the tenant side, they have their own VPC, and they can have their many VPCs. So the detection between the VPC and the detection into the VPC should be detected. And besides, from the administrator side, they should detect their logical network and the physical network. Here we give the example of the process of the detection. From the see in the picture, from the application network, we should detect the VPC VPC such as the vBridge to the vRouter connection. And from the administrator side, we should detect the endpoint to the gateway connection and the endpoint to endpoint detection. Here, the detection between the physical layer are not included, as we think that it can be realized by the traditional mechanism. So come to our consideration. Are there some traditional mechanism extension or the new mechanism for the application network and the logical network detection? And from the detection, we should get some performance indicators such as the packet loss and the time delay. Then how about these performance indicators of the application layer and the logical layer? The third is about the fault location. As there are many levels now, from the detection, we can find the fault in the network. Then with the topology of each layer and the relationship between each other, I think the fault should be precisely located. Next is about the log and alarm. Also, log and alarm of physical network can use the traditional one, while the application network and the logical network, maybe they have their not defined the log and alarm. As I listed several splitted considerations about the network management, so come to a short summary. The first is about the management architecture. We think that the management should be deployed in the application layer, but how to use, what can be used as the management tools, telemetry or something else, I don't know. And the second is about the information collection platform requirement. We think it should be extensible, standard, and with high performance. And the next is about topology. Topology of several levels, now we think it should be visualized. And about the monitoring detection, and they can be divided into several levels also. And the fault location. And the last is the log and alarm of each level. Here I listed some reference, maybe some draft, I think, which is related with the network management, but they're in a separate work group, such as the routing work group, the SFC work group, the LAN work group, and many others, such as the R2RS work group with the fabric topology and many others. As the topic of the network management is very large, and we can see that many drafts is related with this topic, and we think it may be better for us to find a way to combine or integrate all this technology together to make the network management better or some in a more convenient way. Next step, this is a draft in the work in the research work group. So next step, we will narrow down of the content of this draft in order to align with the research group charter, such as make some provide some management principles and management models. The next about suggestions, comments, and maybe the experience of the network sharing. Many thanks.
Okay, so I think we have time for one or two quick questions or comments.
Maybe it's too early in the morning.
Okay.
I'm sitting in the corner on the desk. Maybe you can ask me after the conference. Thank you.
Thank you. This one is Bangladesh, right? So our next speaker is on its way. If you want to take the controls here. Yeah.
Thanks. Good morning. My name is Evangelos Haliplidis, and on behalf of my colleagues, I'm going to present. Is better? Oh, good. Right. So I'm going to present some ideas and some techniques that we have used for the management and operation of NFV and SDN networks. Right. So it was very interesting, and I was very excited about this meeting today because we have been discussing about SDN and NFV and SFC as this kind of combinatory tools and architectures that are able to provide a holistic management of networks. Right. If we go deep down at the network from a softwareized perspective, we can see that networks are all about resources, right? There are many types of resources. And these architectures and frameworks each provide one part of management of these resources. For example, SDN is all about controlling and management of the resources, while NFV is all about the life cycle of these resources, how we are able to instantiate new resources and destroy them. And SFC is about taking these resources and putting them in a chain in order to provide services. So, a brief recap. So, can I have a small show of hands who hasn't read RFC 7426? Who hasn't read? Hasn't, yes. Okay. Okay, nice. So a lot of people in the room have read. That's good. So in the Sdnrg, we have defined an architecture and terminology document that specifies the planes related to SDN and the abstraction layers, right? So we have devices which are composed of resources, and we have defined two types of resources: forwarding resources, where are components of devices that forward traffic, and operational resources, where we define resources other than forwarding, for example, compute resources or storage. We have abstraction layers on top of it, and we have control and management planes which can have services and application, and on top of them we have the application plane and services and applications there. Just a brief note, this is not the architecture, this is a architecture for SDN, right? So we can stack these planes on top of them and create some kind of hierarchy. So if you take a look at SDN and NFV, SDN is about controlling and management of these resources, and NFV is all about instantiating using some kind of hypervisor, making VMs, containers, what have you. And we can control and manage using SDN techniques. Right. Now, we try to just juxtapose RFC 7426 on top of the NFV the HCNFV architecture, and this is a first attempt, right? So please free to comment, and we can discuss upon these aspects. One of the interesting aspects when we tried to do this was that some patterns were emerging, right? We had recursive type of these planes. For example, we have physical resources. We control them using controllers and managers from the Vim, and then on top of them we have another plane of resources which are the virtual, and then on top of that there are another resources for the VNFs, and then controller management plane for the MS and so on. Right. So, based on previous implementation experience, what we tried to do was to see if we can use a single framework for this kind of work, for managing the whole life cycle of a network. And I don't know if many people know this, but we used forces for this kind of work from the IETF, and we split this into two phases. We had an offline phase where you define your functions, what you want to do with the resources. You designed it, define what the operational parameters are, what your capabilities are, what your events, model it, use some kind of translation techniques from model to implement to some initial code, which could be either a compiler, it could be a domain specification language, what have you. And then you compile that, you put it in an element repository, and then interesting things can happen where you can request these resources, instantiate them on a network, and start defining what kind of network you want, what kind of resources you want to implement, what kind of services you want to put on them. Right. So this is a screenshot of a tool that we built in the University of Patras. It's a domain specification language using the forces semantics, where we defined a specification of a resource, and we would then be able to transform it into code, and then be able to use techniques for managing the whole architecture of a network. So, as future directions, what we believe is that it is needed to have a common set of abstractions. Right? We need to see what kind of abstraction we need, possibly a common, using a common framework. For hypervisors, for specific network function, we should start with a base set of these abstractions as a research group from NFVRG, from Sdnrg. And as for applicability, when we defined the RFC 7426, we didn't have network coding in consideration, as it was starting at the point. It would be interesting to see how that affects the architecture that we have defined. So if you have any experience, please free to discuss with us. We could do a follow-up of RFC 7426 and see how current architectures have defined new interfaces that we need to document. as I said before, abstractions for NFVRG, and take a look at autonomic aspects of how we can use these tools and these techniques in order to have a more autonomous network, and that's about it.
Okay, thank you.
Haomian from Huawei. I have a question for clarification. For when you talk about the abstraction models, it's based on the network functions rather than network itself, right? Or because we know there are plenty of work in the IETF talking about network models, including abstraction.
Yeah, there are, yeah. For the net, sorry, can you please repeat the question?
Yeah, when you say the abstraction model on these slides, I assume it is a kind of network function abstraction models.
Yes,
okay.
Yes. There are enough.
Not network model, yeah.
Yeah.
Okay.
There are enough abstraction models already from the IETF. I don't think we need to define a new one, right? We need to have a common set of network functions and hypervisors and what have you.
That's good. Applying the Ockham principle is something that is always.
Sorry, what?
No, simply that I'm saying that applying the Ockham razor is something that is always appreciated. Thanks, Evangelos. So our next speaker is Adrian, that is approaching to our. You want the? Oh, yeah, good catch.
Right, pink box. I'm Adrian. I guess you're a kind of a mixed audience of people who will find a lot of what I say is just a refresher, but hopefully there's some new stuff for you all as well. So what I want to do is talk a little bit about the evolution of the path computation element into becoming more of an SDN control component. This is based on some work that's going on in the PCE working group and in the TEAS, that's the Traffic Engineering, Architecture and Signaling working group. So refresher, what is PCE? Where did it start from? It's a thing that computes paths. That's as simple as that. So it's an abstract functional component that computes paths, and it may be realized as a blob of code or as a function call or as a separate application or a separate server, and it can be built into things or whatever. The purpose of PCE has always been that you need to isolate computation from establishing paths, whether that's established through signaling or through central control. And the benefits to that sort of thing is that you can reuse the function, you can offload the function. So when we were starting this work, we were looking at problems that were computationally too hard for network devices, such as head-end routers or optical switches. And they could then make inquiries off to a server saying, please tell me what path I should be setting up. We started then in packet networks, but very quickly, and actually probably the larger use case now is in transport networks, which may be packet networks or optical networks or anything. So the evolution was, once upon a time, head-end routers did the computation. You wanted an MPLS path. You said, hello router, please set me up a path from A to Z, and the head-end router would compute using its own computation function. So quickly this was offloaded to a server, and then it was pretty clear that an NMS might want to use that server as well to determine a path before it poked the network. And then we evolved into the more complicated case where you have a path, an end-to-end path that traverses multiple domains. Each domain has a PCE that can compute paths in that, and you need some kind of hierarchy so that you can get an end-to-end domain path. So why am I here talking about SDN rather than PCE in the IETF? Well, it ought to be pretty clear that somewhere along the process of being an orchestrator or a domain controller, an SDN system has to work out what network nodes an end-to-end path is going to traverse. So that process of working out the path is path computation. So that functional thing, the PCE, is there in an SDN system. And really the question then is exactly where does it fit in that system? Can we draw it in a box? Can we nail it down? This becomes a little entertaining because I don't think, personal view, I don't think anybody's actually defined what an orchestrator is or really defined what a controller is. So working out where the PCE fits into SDN is debatable. However, it's clear that the function does exist. One other piece of refresher is that as PCE has evolved, it started off as a service where a network node would say, please work out a path for me, tell me what that path is, and I will use it. Along the way, this has become, it's become really important that the PCE should know about other paths that already exist in the network. It's not just the state of the network. So it's become what we call stateful. It has a database of, we say LSPs, but really whatever you want to call them, trails, connections, LSPs, so that it can take restorative action, so that it can know what to do when there's a failure, when there's a planned outage, a maintenance action, or when you want to have diverse paths in the network for some reason. So the stateful PCE starts to do that. And then it's only one more step for the PCC, that is the client, to say, well, I've set this path up, could you please own it and manage it for me? So could you please tell me all the things I should do and actually instruct me? And then from there we go, the network doesn't actually have to be the person that asks. The PCE can just say, set up this path. This would be a good path to have for whatever its reason. And of course, its reason is likely to be a management operation. There is somebody up there who says, I want a trail across the network, PCE work it out and instruct the network what to do. And then suddenly we discover that this stateful active PCE is an SDN component. It's telling the network what to do as software. So where we're going now is to say, can we have a PCE-based central controller? And we've used the word controller because we haven't used the word orchestrator. I've recently heard people talking, getting tired of the term orchestrator and moving on to choreographer. And I want to go further than that. I want to talk about PCE as an impresario. So in these glorious ASCII art pictures, we have two views of the world, and the top one is saying, let's assume there's some orchestration, service manager, OSS, whatever, that says, I want this service delivered. This request is passed on to a PCE-based controller, which looks at the traffic engineering database, looks at the resources available, works out what trails are needed, and then pokes a control plane. It says, okay, control plane, head-end node, please signal these things. So that's sort of one end of SDN. The other picture shows in the middle of the picture that the PCE-based controller, I stepped out the pink box. No, I've still got my foot in the pink box. There we go. The PCE-based controller can actually poke individual nodes. It's using the same protocol, the PCE protocol, PSEP. And the philosophy is if you can poke a node to set up a whole trail, you can poke a node to set up a shorter trail. And a short trail reduces to a single hop, and a single hop is a cross connect, and that's what we're used to doing in an SDN system. So you can do node by node, you can do distributed control plane, and of course you can then have a hybrid system where there's control plane and node by node. You can stitch things together. You have a fully flexible, a centralized control of a network, all using the same controller, all using the same southbound protocol. We have use cases then that demand that you have multiple domains, and this actually fits in with the way PCE works hierarchically and horizontally. So there's actually nothing new in this. It's just to say the centralized PCE control can work in a more than simple network. And then lastly, we've been driving this work from lots of use cases. And as often happens in the IETF, you say, could we have a use case? And you get none for a while, and then you get 100. So this just lists some of the things. Obviously, the control plane operating network I talked about. For ages, we've had statically provisioned MPLS networks, and this is kind of the same thing. Transport SDN has been bubbling up in a lot of other bodies and forums, and so on and so on and so on and so on. Segment routing is a big use case. So you can look at some drafts. The draft listed there tries to pull out section by section each use case. And there was a really nice presentation from MTS Belarus, who came to the TEAS working group this week to say, here is our mobile backhaul use case that would make use of this. That's my 8 minutes of talking, and now my 2 minutes of questions.
So, help yourself.
Kostas Pedikousis, Travel Pink. Thank you very much for the presentation, Adrian. It was really good. I have one minor consideration. I'm not sure if PCE was really the first SDN southbound, from a historical perspective, but never mind. The second thing is that especially if you go a couple of slides back when you have the hierarchical and so on, there has been a lot of work and some drafts as well about this. And to me, it looks like, I mean, I'm not sure about domain 1 and domain 2, because this was like more multi-domain, but it looks like you're kind of retrofitting PCE in the hierarchical or recursive kind of architectures that I have in mind, that have been published in the last few years. So have you looked at the other research I mean, it's a research group after all, right? Have you seen at the other research projects and how they're doing it instead of using PCE and,
Yeah, so I think you're raising from different angles the same question, which is why PCE, well, rather why PSEP instead of protocol foo? And the answer typically is from deployment and from implementation. It would be nice to not implement and deploy 10 protocols.
If you have PCE already.
Absolutely, absolutely. And the tension we're seeing, certainly in the IETF, is probably three protocols all moving into the same crossover spaces. So the three are PSEP, let's say RESTconf Yang or RESTconf JSON or whatever, and BGP/BGP-LS. And I am not going to operate a beauty contest. So what I'm doing in these slides is saying, this is what people are talking about and doing. I'm not pronouncing on whether or not it's good. I would love for the research community to look at these three approaches and say, they are starting to overlap. They're treading on each other's turf, and that's functionally okay or functionally broken.
Mm-hmm.
Performance okay or performance broken. Complexity okay or complexity broken.
Right.
The industry community, I suspect, is not going to do that because all they care about is dollars.
Right. So I get off the tunnel. I haven't followed the recent developments in this. Is there an open source kind of implementation for this? That, I mean, for the research community, I mean.
So there is work that's been going on in to put this PCECC stuff into open source. Dan nods because Dan follows open source, and you might go to the microphone in a minute and tell us which ones. But yes, it's the short answer.
Honest.
Honest. Dan says honest.
And some others as well. So we can talk about that later on.
Okay, Pedro Aranda, Telefónica. You were speaking about the orchestrator becoming the impresario. My question is, who's going to be the prima donna? No, but seriously, what I see here is, you say PC-based controller. Can't we say that this could also be a PC application running on any of these wonderful new controllers? That would actually simplify many things and may even go, can you go back to that slide? Because that may also help, you know, there's all this problems between controllers, SDN controllers talking to one another, and that might be a way of solving many of the issues they have.
Yeah, I mean, this hierarchical cascading is, I believe, getting confusing. And you know, I was being facetious when I said nobody's defined what a controller is, but once upon a time, a controller controlled a device. And at the point that it became a domain controller, we opened this whole lack of clarity about how you build hierarchy. And so the answer to your question is yes. A PC-based thing talks precept southbound. What it talks to, it's just something else.
Okay, fine, thank you.
Thanks, Adrian. So that was fast enough.
Okay, can you hear me in the back? Great. So my name is Tal Mizrahi, and I'm a switch architect at Marvell. I've been doing that for about 10 years now. I'm also an IETFer. I've been doing that for about 7 years. And I've recently completed my PhD, which I've done at the Technion, under the supervision of Professor Yoram Moses. And this topic is about the main topic of my PhD. It's using time in software-defined and centrally managed environments. And actually, it's pretty exciting for me to be here today, because the very first time we presented preliminary concepts of this work was here in this very room 3 years ago in the Sdnrg meeting in the IETF. And we actually got some very interesting feedback from this community. Basically, people told us, that's a great idea, but it will never work. So it became a goal for us not only to show that it's a great idea, but also to show that it can work. Some background. So SDN means different things to different people, but probably the common thread is that it's a centralized architecture, it's flexible, it's dynamic. You have a central entity, which can be either a controller or an orchestrator or a netconf client, anything like that. And in this work, we ask the question, what would happen if all the nodes had synchronized clocks, and if the central entity had a way of scheduling network updates, of telling the switches when they need to perform configuration updates, path changes, and so on. Use cases. So time can be used in network managed environments in general. It can be used for coordinating configuration updates. So you can tell all the nodes to perform a configuration update at the same time. Or you can take a coordinated snapshot where you capture the state of all the nodes, captured at the same time. Time can also be used for updating paths in the network. So for example, you can invoke an update that occurs at multiple switches at the same time. Or you can invoke an update that occurs at different switches at different update times, and this creates a specific order in those switches. And this can be done either in OpenFlow or in the context of I2RS or PCE, forces, and so on. Doesn't matter. Let's see an example. Let's say we have two flows which are forwarded through two different paths, and we want to change these two paths. To do that, we need to update two switches. So let's say we don't update these two switches at the same time. For example, if we update the right one first, we'll run into congestion and packets will be lost. Obviously, that's not good. But if we can update both switches at the same time, we can avoid this congestion. So that's one example. Another example, let's say we want to update the blue path to the green path. To do that, what we typically do is we update the right switch first, then the left switch, and then the top switch. Okay, kind of complicated. This approach doesn't use time, of course. What we can do instead is let's update all the switches at the same time. It's simple. The drawback of that approach is that packets that are en route during the update may get lost. To avoid that drawback, what we can do is we can schedule the updates to be performed at 3 different update times, which guarantees the correct order between these 3 phases. So that's another example. Another aspect we analyzed is not just using time, but using timestamps. And the idea is that if we have a time-stamped domain in the network, all the packets that go into that domain have a timestamp attached to their header, and then when the packets leave the domain, we remove the timestamp from the header. And now, this timestamp can be used by intermediate devices, switches, VNFs, and so on. So obviously, it can be used for measuring delay. It can be used for other purposes. For example, it can be used as a marking method in passive performance monitoring. Or it can be used for taking smart policy decisions like, I'm going to perform action A if the timestamp is within a certain range. So that's another use case. Well, it will never work anyway, right? So one of the most common paradigms we ran into is that synchronization is difficult or expensive. And I think most of us know that's not accurate. Just as an example, PTP is a very common and mature technology to be used today in various different applications. And for example, China Mobile have revealed in the TikTok working group that they have today over 1 million base stations which are PTP enabled. But even that's not enough. I mean, even if you have perfectly synchronized clocks, how do you get these timed updates to be performed accurately at the time they were supposed to be performed? So in order to address that, we propose a method called time flip. Time flip is a time-based TCAM lookup. And the idea, in a nutshell, in conventional TCAM lookups, basically you have the packet's search key, which is compared with all the entries of the TCAM. If there's a match with one of the entries, there's a corresponding action that takes place. In time flip, first of all, we attach a timestamp to the internal metadata of every packet, and now that timestamp can be used as part of the TCAM key. And that means that you can define TCAM rules which are confined to a specific time range. Now, if you combine that with accurate clock synchronization, you get a mechanism which allows you to perform very accurate scheduling of time-based updates. Now, using time ranges in TCAM sounds a bit expensive in terms of resources, right? And the answer is no. Okay, so one of the things we showed in this work is that under typical conditions, in order to implement a time flip, what you will need is 1 bit in the TCAM in each entry, and 1 entry per time flip. Now, it all sounds good in theory, but the real question is, will it ever work on a real switch, right? And fortunately, the answer is yes. So this is a development board of a Marvell switch silicon, and I come from a hot country, so we use big fans. And we've tested time flip on a real switch in full wire speed. It provides a sub-microsecond accuracy on a real device. So basically in this work, we analyzed various aspects of using time in software-defined and centrally managed environments. And from a practical perspective, we designed a new feature in OpenFlow, which allows you to perform time-based updates. This new feature is now part of OpenFlow 1.5. And we also designed a time capability in netconf, which is now an experimental RFC. There are also open source prototypes available for these components. So going back to one of the first slides, actually the technology for synchronized clocks is already there. And based on our work, the infrastructure for experimenting with time-based updates is also there. So now we believe there's a lot of potential for future work here. First of all, timed updates are certainly something worth considering in the context of netconf, restconf. It's relevant to I2RS, to PCE, to forces. Data plane timestamping is already being considered in the SFC working group. We're taking part in that. And it's certainly interesting in the context of, yep, that's the last slide. It's certainly interesting in the context of overlay protocols in general. And finally, if you're interested in some of this stuff and you want to talk to us and potentially collaborate, we'd be happy to do it. And by the way, we believe that it does work. Thanks.
So,
Stuart Bryant. So this is excellent work, and it's long overdue. From a number of us for many years have thought that decent time synchronization, particularly those of us on the 1588 project, would dramatically simplify network architecture and protocol design. However, I'd like to go back to your idea of flipping the forwarding on a schedule. When Mike Shand and I were looking at loop-free convergence, we proposed such a scheduled changeover. And the problem that we had was everyone was concerned that it effectively doubled the size of the fib. And I think of course it does that, because you need one entry for the old epoch and one for the new. And that was always a showstopper in people considering that, particularly in large fibs for core forwarders.
Right, I agree. So if you want to replace the entire fib, you will need, in practice, to have the old entries and the new ones, and that's true, it's double buffering. But if you want to do it gradually, I mean, each time you only update a few, you don't need the entire fib to be replicated.
The pathological case is always that you have to have the whole thing there in order to deal with a critical failure in the network that requires you to, for example, in a ring structure, pretty well everything gets changed.
Right.
John Dowdle, Airbus. Thanks for your presentation, really interesting. On Monday, I stood in the Delay Tolerant Networks group and articulated a problem that actually needed this to work, which is when nodes are all busy moving around and then occasionally bump into each other at a known time. It's a problem known in DCN as contract graph routing. How do I coordinate all of that? How do I update that in a standards-based fashion? I think about 3/4 of your presentation to solve that problem. So thank you.
Thanks.
Hi, Boris Hassanov, Huawei. Just one remark, maybe. It reminds me debates about what is better, token ring versus Ethernet, sync or async protocols, right? And history shows what async protocol survived. No token ring, no DDI. So I would love to see what this time might be like. Your approach will like break this tradition of asynchronous protocols always win. So let's see.
Okay, thanks.
Okay. So let's move on. Yeah. So I got the good thing is that you are prepared, so this is very much appreciated. If you don't mind, stand on the pink. Yeah. No, stop. Wait.
I'm on the other screen.
Thank you. I'm Frederick Hauser. I'm working for Michael Mann's research group at University of Tübingen, and we did some work on authentication and authorization in wired open flow-based networks using 802.1x in the last weeks. So what was the basic idea behind this? We are currently doing a research project on how to use SDN in our campus networks. And we found out that there's some extensive work going on identity-based network control, like kinetics, resonance, ethane, and many, many other approaches. But we also found out that there's like a lack in the status quo, because most of work done in SDN proposes web front-end authentication as mechanism for authentication today. As you all know, web front-end authentication, like used in public hotspots or in hotels or trains or airports, requires heavy user interaction, especially if you think of things like re-authentication. On the other side, there are some compatibility issues, like we do not have web browsers on devices like printers or IP phones or surveillance cameras. As an alternative, static MAC address mapping is proposed, but I think it's clear that this is highly insecure because of MAC address spoofing, etc. So we thought about why not using 802.1x as a widely used standard for port-based authentication and authorization in access networks. Like I think you know it from EduROM, which is also used here. And 802.1x leverages the extensible authentication protocol and the remote authentication dial-in user service. And we just thought about making this work for SDN environments. So the first step in this process was bringing the 802.1x authenticator sitting on the local legacy switches to the SDN controller in form of a network application. We focused here on being compliant to standards because we wanted the modification to be transparent to all endpoints. In our campus networks, we have about 20,000 hosts, and we have some AAA servers running in the data center. And we do not want to make any chances on all network lines, and we do not want to make any chances on the data center infrastructure. So what we basically did is bringing radius-based authentication in the traditional manner as 802.1x into our network application, where the network application just works as a pass-through device, like known from legacy switches. And additionally, and this should be clear, we do not want to find a substitution for radius. We wanted to provide an additional possibility of using authentication resources, just like directly interacting with a SQL database or an LDAP server for simplified environments, like a lab room where we just want to have a simple protection based on user and password credentials stored in a SQL database. Another extension we made is introducing a session management database, which we consider as a network-wide database for identity-based network control. So we wanted to have like a session database which is based for the control mechanisms as mentioned in the first slide. And this session management should also be used for checking simultaneous usage boundaries to ensure that, well, for example, one class of user can only hold 2 concurrent sessions at a time. This session database supports fine-grained and complex admission rules, like you can allow for specific identities or classes of identities to only allow a particular set of flows or communication rules. And the session management database enforces authorization changes directly. So if like an external network scanner application detects a compromised host, it can signal the session database, which directly deauthorizes the client. So as some kind of summary, what we did, we made a proof of concept implementation for Rio SDN controller. We built various test scenarios. We tested various authentication and authorization resources. And we plan on doing some kind of performance study to see how it needs to scale for large enterprise networks. We want to think about using network function virtualization to provide scalability. We want to open source our current implementation, and we want to provide some in-detail documentation on how this overall system was built. Thank you.
Thanks. It was really fast. So.
Thank you for being very efficient. A question, have you deployed actually this on the campus? Or, I mean, you made a proof of concept implementation, but it was an actual deployment, or it was just in a lab? Or
it was just in a lab.
And do you plan to make a real deployment?
I think we will try to make in the next step some bigger test scenario, but maybe if it works out, I think there's some possibility of rolling out just in our faculty to get a bigger test case.
Okay, thank you.
So, and this next, I don't have to check the agenda because
do I use this or?
If but wait till Loante tells you, because otherwise you're controlling his browser. And Andy, the pink square, please.
Hi, my name's Andy Beach, and I'm reviewing some topics related to multi-site NFV network services and challenges in computing optimization. So, I mean, some of this has been touched on. The work that was referenced by the second speaker talked about some of the work of the integrated SDN NFV resource management. The general statement is orchestration with integrated planning algorithms is necessary to achieve optimal utilization of the compute and networking resources. The promise of NFV SDN to the industry is that it's going to save OpEx. Well, we need to do something to achieve that. I guess I'd also couch this. This is a discussion that somewhat references research, but it's also based on current SDO and work in open source. To date, definitions of these in those organizations are defining the optimization algorithms currently are independent. And this seems like a reasonable time to really begin to push for pulling that together, because any enhancements to legacy or future protocols are going to need to be sorted out within the next few years. So again, expected to reduce OpEx, maximize utilization of the infrastructure, keep costs low, meaning if there's multiple options for supporting a service or set of services, use the lower cost as long as you meet your SLAs. Follow whatever policies people have. You also want to minimize migrations because those will affect your SLAs. The trade-off is obviously utilization of your resources versus those SLAs, or providing an adequate service. So currently, these are separated. I am engaged in ETSI as well. It's been separated so far, and orchestration for networks today, SDN and PCE, and I guess they mean the same thing, or I should just have a unify symbol there, are independent from the NFV management. So those planning competitions need to be unified or cooperative. So the activities that we have been engaged in is reviewing use cases, reviewing research papers on addressing some of these use cases. Again, current SDO and open source projects, what they're doing, studying lifecycle management for these, what the roles of the different functional blocks would be in supporting this, what information needs to be passed among these, and looking to see what we can do to push requirements towards either legacy or new protocols. This is fairly trivial example of applying one service. If you have independent computations, you can come up with a solution that fails versus if you bring it together, they work. I won't go into that too much. The more interesting use cases that we've been looking at are not single service end-to-end, but when you have something where you need like a virtual CDN, especially like a flash mob or some sort of emergency, something where suddenly there's a large volume of resources that need to be supported, either from a sensor network or from some sort of a CDN solution. What the implications are for that in order to support something like that in a very rapidly and utilize your networking and your data center resources quickly. So we are studying those use cases and studying what's been going on in research and sorting out what the implications are for knowledge representation to address those quickly. And then this is, I won't go through this too much for time, but again, if you have a migration, it's similar to the other. You need to solve this very quickly and make this happen and avoid outages. So we're doing this in NFRG, presenting these use cases in a document. This is really just a quick review of what's going on in open source today. And this is as much a presentation to call out that the open source should be looking at this issue. Today they're separated. OpenStack tells Open Daylight, I've got this, now please connect them. Etsy has its, people don't usually look at this because Etsy never really talks about wide area network or support across networks, but there is an architecture that's being reviewed there now for figuring out what the connectivity control solution should be, but it's currently not looking at optimization. These are Etsy figures, so I'm using their nomenclature. Today they are looking at orchestration solutions, either an end-to-end orchestrator above things, but they're still separate. I would, or a hierarchical from an orchestrator for NFV, then speaking down to the WAN manager. Let's go back for a second. I'm calling these out because this is also the architectures. It's an Etsy figure, but it's architectures that are being used in the current open source. There's many. There's OpenO, LSO, TM Forum, the many different names from the top level. Sonata's running this way. I know that they're thinking about this but aren't doing anything yet. And then Etsy also talks about hierarchical, and this has not been fully developed, but this is looking for distributed solutions for solving the problem. My comment is essentially that some of those are morphologically or architecturally the same, and really if you just look at it, you're looking for optimized integration with all of information and policies, your instances that have been deployed, the topology and the available resources, and you need to be able to figure out what the best, and our interest right now is in the use cases, and then looking at what the information flows are necessary and what the knowledge representations are in order to get a fast response. I didn't really come here, I came here prepared to say this is what we're doing and looking at use cases, and next steps are some of the architecture and the knowledge representation issues, because you need to have very fast response time, so you're looking at pattern recognition and things like that. I am interested in following up in the SDN work and some of the knowledge representation there, because I haven't looked at that in a while. And then pushing this to development requirements. I think earlier Adrian had been asked about why PCE for some things. We're interested in what's necessary to support this for legacy as well, or integrating on running networks. So next steps, continue use case development requirements, looking to coordinate with others. This will touch on a number of different work groups. I did not list the RGs, but obviously work that's going on in the RGs. So that's it. Oh, actually, almost that's it. I did want to point out, so, sorry. One group that has done some work, there was a presentation yesterday from Alto that actually described some ways of using graphs to represent things that was interesting. So I recommend taking a look at that.
Right, so Deng Hui is speaking for the Open Orchestrator. I'm the chair of the Open Orchestrator project. So you mentioned here. So that project is try to integrate both SDN orchestrator and also MFE orchestrator. So what I see here, you are talking about to put the agent into separate MFE orchestrator or the SDN orchestrator. Is that what you are planning?
I'm saying more historically, it's history, but you have a PCE or SDN controller that has not had to think about orchestrating, what the concerns are, what if I'm going to deploy a virtual network or a network service, VNFG, across multiple data centers, what the resources are available at those, as well as what's going on in the network in order to, where do I deploy that? And there's a number of constraints involved. You're saying you are integrating the consideration for that. Is that right?
Yeah, so look at the use case of Open Orchestrator project. You can see we are really doing similar thing you are describing here.
Okay.
Talking about IETF's work here, I think we do have the drivers for the like layer 3 VPN, layer 2 VPN, and also if you talk about a PC, previous speaker talk about the supercontrollers. They have the drivers for that part to interconnect the data centers, what you call it data center.
Sure.
So then I see the challenges would be the border issue, how you really mapping between, within the data center and also like NetLink for interconnect the data centers. So that's the technical, problem that we are solving today. So we try to upgrade, to the orchestrator layer to solve the interconnection issues, across the SDN domain and also MFE domain.
I guess, okay, and I'm interested in understanding more about what other things are doing. I think the challenges here are the response time. There cannot be a lot of interaction between agents before being able to present something. So it sounds like you're saying you have everything in one location, but if I need to go to the PCE to find out what can I get here or whatever, it may take time. So I'm interested in what's necessary in order to potentially have that information available, represented in a database or knowledge base, to be able to rapidly provision or provide the path, identify what the data centers are and where the VNFs are, as well as meet the policy. So it's sort of what information do I need to receive from the SDN or the EMS or whatever you have to support, to be able to have a place where I can compute that path quickly.
Right, so I recommend you to log in, to the wiki page of the Open Orchestrator page. So if you have the Linux Foundation, that's free to join.
No, I understand, but you've been open for maybe
there.
2 months. I understand. I've been mainly looking at research algorithms that people are using for HPC or VCDN or sensors, understanding what the algorithms that they're looking for commonality for being able to do support this as well as a fast response time. I'll certainly look at the use cases that you have. Right, there's a number of open source projects, and if you're looking at that, that's great.
Yeah, I try to encourage you, help you to understand better what we are doing.
Right.
Yeah, that's
no, like I'm saying, though, OpenO.
Sorry, Andy, if you can continue on this, offline.
It's all offline.
Okay, thank you.
Thank you. Next one. Oh, surprisingly, next one is not already. Okay, you're here. Perfect. This is. Sorry, no, I didn't see you in there. So.
Hello, everyone. I'm Yimeng from Datacom Paris Tech. Today, my topic is SDN controller performance evaluation. And this work is cooperated with ANR Reflexion project. Since SDN adopts a relatively centralized control plane, the performance of controller is critical to the success of the whole system. And the development of SDN controller still has following challenges. So first, the SDN is still evolving in a faster pace. More and more functions are integrated into new open flow specifications. So this is hard for developers to follow. And second, SDN is gradually deployed in more and more scenarios. All these new scenarios propose new requirements, such as support of network virtualization or network security. And third, in order to improve the performance, we have to first accurately evaluate them. But right now, there are really few benchmark tools or framework for measuring them. Fourth, the distributed controller is proposed to address the scalability problem. But as all the other distributed systems, it's really difficult to provide high availability. In this presentation, we aim at providing systematical evaluations on SDN controller. So the evaluation starts from centralized controller, and the 5 open source controllers are chosen, namely POX, Linux, Flatlet, and Bacon. And the following table shows a baseline performance. In this scenario, each controller runs as a learning switch, and only one CPU core is provided, and the one switch is connected. And from the result, we can see that Bacon outperforms others by far. It can achieve 2,300 responses per millisecond, while Knox and Flatlet can only achieve 1/3 of Bacon's throughput. And as expected, both Python-based controller POX and Liu can provide least throughput and the largest latency. And beyond the baseline performance, we also investigate various performance factors, such as the impact of number of switches, the number of threads, the impact of system-wide settings. We also design several specifically crafted scenarios for more testing. Let's see some selected results. So first, we notice a significant performance degradation on all controllers when the number of switches is over 200. This implies that the centralized controller is not suitable for large-scale deployment. This is why and where a distributed controller is needed. Second, by applying an alternative pattern interpreter, PyPy, both POX and Liu can achieve 4 times performance improvement, and compared with default C pattern. And during the evaluation, we didn't see any side effect yet by using PyPy. And third, when enabling hyperthreading, both Bacon and Flatlight, 2 Java-based controllers can achieve 10% performance improvement. And the fourth, we notice a correlation between the throughput and latency. So there's a trade-off between them. So we take Bacon as an example. The following figure shows the correlation between its throughput and latency. And in the figure, we can see that when the throughput achieves at its maximum value, the latency is also enlarged thousands of times compared with an empty buffer. But luckily, on this curve, we can still find the selected point as marked with black point. We can keep the latency within 0.1 milliseconds, as well as provide a high throughput. And for completeness, we also evaluated 2 distributed controllers for comparison. The results shown here. By running on single CPU, we can see that their performance are greatly constrained. This means they have to run with multiple cores and in a cluster mode. When running in cluster, although multiple controller nodes are geographically distributed, they still act as a centralized control plane. In order to function correctly and consistently, the synchronization and coordination among control nodes are required. So this introduces a new type of control traffic. We define this as synchronization traffic. And of course, the additional synchronization will introduce new control latency to the system. And due to its importance, we studied the characteristic of this synchronization traffic. So we take all nodes as example for investigation. We choose version 1.1.0. In this version, The synchronization is implemented by the open source library Hazelcast. And we list some results here. We first check the total volume of synchronization traffic. We find that the peak synchronization traffic rate is always less than 150 Mbps with 5 nodes. This volume can be neglected compared with modern high-speed link bandwidth. And we further check the flow installation latency. You can see that with 3 nodes, the flow installation latency could be enlarged by 2 or 3 times compared with single node. And during the evaluation, we also find the resource contention among when the controller is processing various control messages. Now, in existing OpenFlow specification, all control messages are processed equally by a simple first in, first out queue without priority thinking. But for 2 different type of control messages, for example, flow add and packet out, which one is more important? It really depends on the real requirements. And this problem will become more complex in distributed controller because flow add will trigger synchronization among multiple control nodes. And the distributed controller also adopts a 2-layer synchronization scheme, which means the controller nodes must first confirm that the rule is already installed on the switch, and then he will synchronize this information with other nodes. So based on this scheme, flow add seems to have a higher priority in the consideration of synchronization efficiency. But this answer could be changed in other scenarios. Finally, to the summary part. The performance is no longer the only dimension for choosing controller. The usability, reliability, and security are equally important. And the centralized controller show clear limitations on large-scale deployment, and distributed controller are usually required. Third, the success of a distributed controller is based on an efficient synchronization system, and the various modifications are required, such as a priority-based control message processing system. And fourth, we also noticed there are several related IETF drafts that are working on the similar directions. The first one is benchmarking methodology for SDN controller performance, which aims to regulating controller benchmarking. And the second is priority-based flow rule request message processing mechanism in the OpenFlow switch. And they mainly focus on flow rule request message. And we expect that priority design could be extended to all control messages. And finally, right now we still like available benchmark tools to provide in-depth results. And I think this could be done by following above-mentioned benchmarking drafts. And that's all. A question?
Okay. Good morning, Pedro Aranda, Telefónica. Can you please go to slide 3? Yes.
Okay.
You start by this controllers, looking at them, the only one which more or less seems like active and not very much as Floodlight because Unreal. And then you try to compare here things that are written in Python, things that are written in C++, things that are written in Java.
Yeah.
You also said something about PyPy versus using CPython. So too many things to compare. You're trying. My feeling here is that you're trying to compare like potatoes with bananas with cakes.
Okay.
Jimeng, if you don't mind to go back to it. No,
because I cannot.
You hear better if you get there.
So I just come close.
Okay. No, but just.
Okay, you think the comparison is not that fiery because we involved that so many factors involved. Yes.
Yes, I'd need more data to understand these comparisons.
Because I just try to exploit all the potential for each controller because for different controller, the suitable scenarios is also different. Yeah. So I just try to exploit all the potential for each controller. And,
Yes.
and this comparison is just used as a reference to get a basic idea.
Yes, but again, I have my doubts on this comparison.
Thank you.
Boris Khasonov, do you have somewhere like detailed test report?
Yes, I have this.
Can you share a link somehow?
Yes, I can send you an email about related paper. Okay.
I mean, if it is an open report and you feel like, well, I was about asking him to share it on the Sdnrg list, but I don't know if would be the chair. You're the chair. So.
It might be added to latest version of the slides link.
No, not the latest version of the slides of the report itself. What are you asking for?
I think like it would be better to update the slides and put like informational.
No, exactly. So have a link to the report there. If you have a link.
Yes.
To the report, just to share it with the.
Okay.
Yeah.
Hi, Samuel Jarrell, Purdue University. So what I feel like I'm missing in this presentation is what you actually did to get these numbers, right? You presented us with a bunch of numbers on throughput and latency, but are we talking here about like learning switch routing or, because it makes a huge difference on the numbers that you're actually going to get that way. So can you tell us a little bit more about the methodology that you went to generate these numbers?
You mean the methodology?
Yes.
Okay. Fraud measurement, part of measurement is based on the Cbench, you know this.
Yes.
And part of based on the Open vSwitch. I use several Open vSwitch to generate packet request. So it's a combination use of both them.
Okay. I mean, I guess I would strongly encourage you to look at some more realistic testing methods.
Yeah, I know.
Cbench is really great for just.
Yeah, Cbench is emulated switch. So it's better to use real switch to do this. That's why I mentioned we need more realistic benchmark tools.
Okay, thank you.
Sarah Banks, NetScout. So to echo what Diego was asking, as author of the SDN controller draft in BMWG, I too wouldn't mind understanding a little more about the methodology that you used.
Okay.
If you took a look at any of the test cases that we outlined in the SDN controller draft, that might be helpful. And then to echo what Boris is saying too, I would like to see the detailed report. So if you work it out that you're going to send it to Sdnrg, great. Could you send it to BMWG as well?
Okay.
Yeah? Thank you.
Thank you. Thank you for your advice.
Last one and brief, please.
Sorry, Uriel to Intel. Not to pile on the other comments, I think you may want to have other controllers here, but two important comments. One is that testing a controller in isolation without having, say, end stations is really very theoretical. The other one, in order to allow the community to make sure that we understand the results correctly and make sure that they are reproducible and that we all see what is the root cause, that has to be added. So when we have numbers, it would be really wonderful to add another column that says, and the bottleneck was X, because that would allow us to correlate results and make sure, for instance, you mentioned you're using OVS, don't know what version, maybe OVS was the bottleneck, and that skews some of the results over here.
Okay, thank you. Robert, hey.
Need to check where is blue sheet. Okay. Who do not sign yet, please sign.
Good morning, everyone. Everybody, sorry. Everybody has signed the blue sheets? Everybody? No, the second is there. So, oh, we only have, that's, yeah, a few of you. That's good. You're extremely disciplined. Sorry.
Oh, it's okay. Thank you. Good morning, everyone. My name is Robert Sabo. This is joint work with the University of Campinas in Brazil that we are doing in VNF benchmarking as a service, but primary VNF and benchmarking. So what is this topic about is on the right-hand side, you can see an exemplary scenario where using the SDNFV nomenclatures. So we have network function virtualization orchestrators and different VIMs, and then we have NFI VI infrastructure, different POPs, and then the different POPs could be based on different execution environments or different technologies, for example, a container OS based, an Ntense hypervisor, or a bare metal. And the problem comes with the VNF deployment or the network service deployment, because if a customer asks a network service with the definition of a VNF forwarding graph, then the NFVO must deploy this in a way that it is known in advance. If we pick one of the deployment option, what will be the performance? So the orchestrator must know in advance what it might expect when mapping VNF to one of the locations. However, the different NFVI POPs can evolve in time, so we can change, upgrade the CPU, upgrade the memory, or we add access something like hardware acceleration, or we just change the technology. And also the VNFs can evolve over time. For example, there's a new release, there's further improvement in the VNFs. So the problem is that we have a very dynamic environment where both the deployment targets and also the VNFs change over time. And we still would like to have some deterministic behavior after the decisions at the NFVO. So the orchestrator must know something like about if we pick one VNF with one flavor, for example, CPU memory storage assignment, what would be the given KPI value that we can expect that the VNF will perform at a given location. And in order to do this, we need to know and we need to collect autonomously or in an automatic way some benchmarking information related to these cost of deployments. And that is the target for benchmarking as a service. Okay, so the way we would like to do this is to extend the existing architecture, for example, the SDNFV or other architectures dealing with the virtualization space, and basically to add components that can interact with traditional NFV orchestration via a virtual VNF benchmarking as a service API. Okay, what are the components here? So what we expect, this is just some insight into some preliminary research ideas, is that we can define a VNF benchmarking information base where we can define benchmarking methodology for the VNFs. So this would be a primary input for the VNF benchmarking as a service, and this is fed by the VNF developers, because each VNF realizes one application, but at the end of the day, we would like to assess how such a VNF performs at a POP on a low-level abstraction, like if we put it into an end-to-end VNF forwarding graph, what would be the throughput characteristics, what would be the latency introduced by that VNF. So at the end of the day, we are interested in measuring a VNF that is developed by the developer over the POPs for characteristics which match the networking and the compute part. So we would like to establish an association between the software resources and the networking resources. So one possible target would be that VNF1 would allow the incoming rate of 10 megabits per second with latency lower than 200 milliseconds over two of its ports. So it can be defined per each VNF port car at POP1 with 2 CPU and 8 gigabyte memory. At POP2 with 8 CPU, 16 gigabyte memory. So these kind of associations we would like to establish so that when a request arrives, then the NFVO can pick at which POP, what kind of flavor it has to deploy in order to have some expectations on the performance. Okay? Otherwise, we just deploy and we measure real time, and then we have to migrate the VNF to a new location if the performance is not met. So we would like to establish some pre-know-how, a priori know-how about the performance at a different POP for a VNF. Okay, so let's see the approach. So how do we want to do this? This is a slightly different view of the same figure showing some other interfaces. So basically what we receive in a hierarchical architecture, so this could be a customer, we just receive a VNF forwarding graph. And if the VNF is not known at the various potential places where it can be deployed, then the NFVO could pass the original VNF forwarding graph to the VBus service. The VBus service, the VNF benchmarking service, consulting the information base for the benchmarking, could make a deployment request for each of the VNFs, for each of the deployment options, if they don't exist already in the database, in order to evaluate the performance characteristics. This deployment option, however, is nothing else than a VNF forwarding graph, but specific to that VNF, we would like to deploy monitoring components, manager, monitors, and different agents in order to assess the performance of a VNF at a given port. So what we do here is that, based on the original request, we define various VNF forwarding graphs to be deployed, and these forwarding graphs to be deployed contain the manager, agents, etc. And at the end of the day of the process, we will get a report of a VNF performance with a given resource characteristics at a given POP. So that is fed into the information base that later can be used by the NFVO in order to make a decision where to map such a VNF over the infrastructure. Okay, a note here, how does this relate to the SDN? The VNF that we deploy can be a split VNF where the control and the data plane is split. So when logically we request a VNF placement, it might be that there's just a data plane entity which maps directly to an SDN network element, and there's a control plane entity. The whole thing is transparent. So if we would like to assess the data plane performance, and if the data plane is mapped to an SDN network element, then we have to assess basically the data plane performance of the network element, how it was mapped. Okay, enough of the ASCII art. So in a high-level picture, just to show the overarching operation. So if we have a customer requesting a VNF forwarding graph, then the NFVO or the VNF manager consults a network function information base where we expect such profiles to be stored. For example, VNF1 at a given POP performs the network and the network KPI and the software resource association. I performs with a given characteristic if the requested flavor, the requested resources are given. With a different resource set request, the performance will be different. So if anything is missing from this network function information base for the deployment, then the NFVO can consult the VBus service in order to realize this profile. So just to extend and add additional information into the network function information base. Then, as previously mentioned, the VBus entity will make basically the same type of request as the customer request. However, it will be specific to the system under test, which is a specific VNF at a specific NFVI port. Perform the measurements, get the reports, and then feed it into the network function information base or some database, which can be used the NFVO in order for the deployment options. Okay, so before going forward, this VNF benchmark element could be placed anywhere in the hierarchy. So this could run by the customer, for example. If I'm a customer, then I can request a single VNF placement from my provider in order to assess the VNF performance. So I can do it on my own. So this service can be up here at the customer. This can be at the provider level, or this can be at the VIMs, and then the VIMs can report basically these characteristics a priori when creating the domain abstraction. Okay, connections, running short in time, connections to the different activities. So it has connections to the resource orchestration and management, and this we discussed in the NFV-RG research group. Then it has connections to the DevOps cycles, as VNF developers must provide these benchmarking profiles in order to automate this process. Then for the networking and for the network control, what we would like to do is to deploy these test benchmarks as basically service function chains over the NFII and the SDN infrastructure. And then we have some drafts for the benchmarking methodology for the VNFs at a given NFVI POP to the benchmarking working group. And there are some related drafts on this topic. Thank you for your attention.
comments? Yeah, a quick one, no. Yes, I think so you can jump on the. No.
That was an interesting approach. Yeah.
It is not. It's not an ambush, Uri, at all. So.
Yeah, no, I was wondering if he's about to run to the stage. Uri Zur, Intel. I have one question. Is that mainly trying to measure the performance differences between deploying a given VNF in different data centers? And if that is the case, then do you need to go to the resolution of a given NFV, or really is it the difference in deployment between data centers? So in other words, you may need to distinguish between what is the network latency performance component to what is the performance characteristic of a VNF sitting inside a data center given a specific infrastructure that was used.
Yes, exactly. What we envision is a completely distributed cloud, so edge computing and all these associated with that. So you really have different deployment options, and at various places it might not be the same technology that is used for the execution environment. So we might go for an ARM deployment, and certainly we are limited in performance in such devices, but we need to have an assessment. So if we pick that option because of other characteristics, other requirements, for example, we have to place something really close to the end device due to delay requirements, then we might go and place something on an ARM hardware, while if we are more relaxed in the delay requirement, we can put it into the central cloud. But these are different characteristics. So the orchestrator must know how much of these VNFs can be placed there and what resource allocation should be associated with those placements.
Yeah, so it sounds like we need to maybe separate it to two components. What you get between...
Sorry, if you can continue offline, because otherwise...
Okay,
sorry.
Yes. Yes.
Go for it.
I think I'm going to get it better like that. Good morning, Pedro Aranda, Telefonica, and I'm going to go in this presentation about basically what challenges I see in the whole area, overarching the three working groups. And it all starts because we have, on one side, programmable networks, and on the other side, there's lots of virtualization around. So, yeah, lots of enablers. We are talking about that, new opportunities. Everyone is very excited, but also a lot of challenges and requirements if you want to really control and manage the network correctly. So things that I see, for example, is we're going to have more versatility and more automation, but that will also imply new interaction and control models. Therefore, what we are actually needing here is a management solution that will allow us to confront all these needs. So foreseeable paths, I see three, and not in this order necessarily. One is you have the network functions. The network functions can be used as software libraries to build things on top of that, and that goes beyond what you can compose with a service graph. Once you have this, you also need to have a better abstraction of what is happening in the network. And last but not least, there is a current trend, which is machine learning. If you train a machine correctly, you can delegate on it many of the tasks which are currently either being programmed or being done manually by a human operator. So composability of network functions, also known as network application composition. We had a paper in last Saturday's workshop on that. Purpose is to integrate what we have as network functions into a software design cycle that can be applied to networks. So application, the SDN applications work and mainly you have written them, they work, they are proven, so why throw them away if there's any sort of enhancement? Why not evolve them? Why not reuse them? And for that, we have done some tests here in a project called NetID, which was actually the one that was presenting last Saturday. It's sort of an evolution of the SDN architecture based on architectural concepts of the ONF. And as you see there, basically what we are doing is we are mixing some of those smaller and not so powerful controllers facing the network. We have some more powerful controllers, and what we can do is actually compose applications. And this is something I've also seen in I2RS. So actually, this boils down to something to any kind of multi-head environment, where you actually have multiple independent applications that are trying to address the same network resource. And yes, of course, that at the end, if you have many people trying to talk to the same resource, what you end up is having out conflict. And simple example, two applications try to set different next stops for the same prefix in the same box. Who's going to win? So is assigning just a priority, application A is more important than priority B enough or not? Other implications we also see is that this kind of composition things may make you write SDN applications for different layers in the network, and then you can compose that. That simplifies a lot the design of network elements. The problem here is semantics. Even within OpenFlow, as a small example, if an application you write for OpenFlow does not respond, what the hell does that mean? So, and that's not only in OpenFlow, but a small example there. Next topic would be then, if we have all this, why not integrating here some machine language conflicts? So we have lots of SDN controllers or controllers in general. They are gathering a lot of information from the network. We really can use this information in a really intelligent way to manage our networks. However, if I'm saying really intelligent, what does this mean? So one thing many people seem to be forgetting is that intelligent behavior is also learning from the past in order not to repeat the same errors. So since we humans seem to have a hard time in doing these things, why not using machines who have no sentiments and so on to do these things? And of course, if you do that, there's all this development in machine learning that we could use to solve complex issues in the network management. And of course, if we have, so what we have is the SDN controller gathering input events, gathering statistics. And if we feed all this information into the machine language, into the machine learning system, then what we could train to detect complex events. And that is something that is much more complex than just an application implemented in an SDN controller. And the thing is that this trained event can actually talk to different apps that would be running or should talk to different apps that are running in different controllers that are multi-headed and have conflict, to go back and to start talking about things that have already appeared in this presentation. So the next thing is we need some sort of language or some sort of standardized way of talking to these applications. And this should be very high level. And then in comes the next buzzword here, and this is intent. Intent as a possible way of just representing those high-level actions you want to apply. From the machine learning system. So I will try to be a bit provocative, but not too much. What is a non-intent? There's lots of things around. I've seen people calling Java, Python libraries to write applications for SDN controllers intent. For me, that's a non-intent. This is just a medium or low level of abstraction of what you're doing in the controller. It's really not the level of abstraction we want. And the other question I would like to make to all these people that talk about different libraries being intent is that what purpose do they serve either in the northbound interface or in the southbound interface of an SDN controller? So I've seen here something which sort of made me laugh a bit. So some people say intent is a framework to express network control desires. Is this the 50 shades of gray of networking? But the model, I had a second definition, which I liked a bit more. It's a model to describe requests to alter network behavior. That's something that I sort of start to be more comfortable with, but all good and nice and a very good step in the first direction, as long as what we get out of this effort is not yet another library. So SDN controller independent northbound interfaces, yes, we need those. We need to focus on semantic model and data models. Semantics is very important here. There are people there currently. Also, another hot topic is whether this should be just declarative or should be imperative. I think they should be declarative, by the way. But anyhow, this is something to be discussed. Another thing is, should this northbound interface be not only human readable, but also human understandable? And here I have a small example called the Nemo language, which was nice in the sense that it is simple and allows you to have an early adoption of things. That we are still defining the language completely, but I like the approach of going really minimalistic. Like you can define an enormous language with all kinds of constructs, but with 20, if you have a 2080 rule, that's it. And the other one is the ODL-NIC, which is doing the same, but in Yang. So as a conclusion, this is the three things I've been talking about. Is that the right way of doing the cycle, or should we do it the other way around? I still don't know.
Thank you, Pedro. Comments? Questions? You have had enough for the day? Artur, you are coming to take the token, right? Okay, thank you. As Laurent has reminded me that you have -1 minute.
Okay, -1.
Yeah.
Okay, so let's go to lunch. Okay, hi, Artur Hecker from the Huawei Technologies European Research Center in Munich. So this is common work from our research group, it's not only from me. We here try to argue for control as the least common denominator for the future networking. So what we see is a change of paradigm in a way with this programmability. So if before we were designing essentially networks to provide specific services, so by whatever, deploying specific stacks on the devices involved, by providing, of course, the protocols that correspond to those stacks, then by deploying specific topology and configuring all that and so on and so forth, you know all that. It kind of goes in another way. Today, we have an infrastructure. I'm calling it a network here for simplicity. And essentially, the services of that infrastructure with programmability are supposed to be programmed later in the runtime, right? So that is the kind of general way to look at programmability of infrastructures. And this change, of course, is nice because, you know, for customers, maybe it's nice they do not engage in something that you already offer to them as a service, but rather they can actually add services later. So the promise is okay. However, of course, it comes with a price, as always, and this price is, of course, related to this software brittleness, as Steve has put it once, right? So the point here is that we also witness a change, not only in dynamics, but, you know, we go from the code, which has been crafted by vendors for specific devices to some kind of integrator code, which essentially spans all kind of different devices and which has never specifically been tested for that. It's hard to test because essentially all those applications, and we have the examples in SDN, we have the examples in NFV today, essentially are running on something they were not really tested on, right? It's not the same process. So that brings, of course, also with the cyclomatic complexity, which is, a measure for complexity of the software pieces, a lot of challenges. So how do we make these kind of environments actually stable, resilient, working as they should? So if we just go back for a second to, for example, OpenFlow SDN, we see that, okay, it kind of falls short of that promise, right? I cannot achieve this general programmability. So most people are aware of this chicken egg problem in SDN. SDN promises you a software-defined network, but in reality, it of course relies on the existing legacy networking very much. The effect of that is that today's switches essentially are all hybrid switches, right? You need to implement TCP/IP, you need to configure all that, and the programmable thing there then is only the traffic switching, right? So it kind of falls short of the promise in many ways. It doesn't really come up by itself, and it still presumes a lot of specific functionality in the devices which cannot be programmed away, which cannot be changed. So that limits the programmability by far. The second point, maybe a little bit less known, so Pedro just mentioned it, there are those self-inflicted errors in SDN. So what Pedro was saying is that one application can contradict the other. Well, there is more to that, right? One application can actually block a port which is used for OpenFlow communications and therefore effectively disconnect the controller from the switch. So that would be disastrous, of course. And I mean, with programming errors, it kind of is very limiting because then you need to test every application specifically, but that, however, depends on the topology and how the switches are interconnected and so on. So it's a little bit complicated. So I'm comparing here the programming model to DOS, for those of you who remember this disk operating system, right? Where essentially you could write an application which, as a first thing, would throw out DOS out of memory. So it essentially kind of makes it hard to use this trial and error programming models, which, as you know, are most used today in spite of the progresses. So the general problem statement with them goes this way. Essentially, in the context, you have many components. So we're not limited here to software or virtualization. You have components in hardware world. You have components which are local or maybe remote. Software components, of course. So some of them are short-lived. Some of them are, long-lived. And what we need to do, we need to bind them to, maybe we need to deploy them as well, okay, fine, but I'm not talking about this management part. But we need to bind those running components, whatever they are, to essentially services as we like them. And if we want to really provide any kind of critical services or whatever, then we need to bind them efficiently and operationally in runtime. So then what is this common minimum requirement to all those components or even the containers executing those components, which would allow us to first, of course, have this programmability. So we need to reach out to all of them and to tell them what they have to do at exactly the point of time when we need them to do that. But we do not want to make this too complex, it's quite obvious. And we do not want to manually deploy anything because that kind of contradicts the assumptions of scale and what the operators might need and so on. So how do we make this programmability simple and usable? So the simple and usable relates not only to the lack of manual definitions, but also to the resilience of the platform per se, which is contrary today to, for example, OpenFlow SDN. But I could cite another example, and if it's essentially the same, right? So what we are proposing is what we call unified control. So this unification goes in 2 dimensions. We would like to first unify on the control plane the NFV and SDN, so the compute nodes and the transport and network nodes. However, we also go vertically. So the vertical integration refers here to the executing container, where what essentially the resource that executes whatever. So that is the support of virtualization and service parts, service elements per se. So what we really propose then is essentially a suite of protocols on the resource layer. So it's resource-to-resource protocols. It's not any kind of central entity, whatever, which are first essentially building and maintaining this actual control. So what we're asking us is, okay, but the question which we ask ourselves is very simple. Okay, so you deploy those components. How do we make sure that they become a programmable network? What is this first minimum thing that must be injected everywhere without overloading them, without presuming too much, but still being, as general as possible? So it's like you can compare it to BGP, right? BGP does the same for destination-based routing in IP. So it has a specific use case in mind, this destination-based routing for IP. We would like to do the same without having that specific use case because we think it might be then later programmed to do whatever, switch source routing or some other things, including stacks. So what we really propose then is to say that, first of all, we can generalize the view on the resources. So we support all kinds of resources. The resources have then this minimum containers. This is this LCD, this least common denominator, which comes, of course, with a bunch of protocols. And we call this an RCA, Resource Control Agent. Why agent? Well, because it's more than a client. And essentially, these things must converge together in a distributed manner to provide one centralistic view, or whatever view you need, actually, for that matter, so that the behavior can then later be programmed by using that view, abstracted view, okay? So maybe I skip this slide. So essentially, the RCA inside has always two phases, right? One phase is it's a peer within this control plane that it establishes and maintains, and the other view that it actually gives you control to the resource on which it's running, okay? And as phases, essentially, yes, all resource elements are, represented by this RCA, which is running on top of the resources. So that does not know any layers, that does not know any, specific protocols. Yes, it can use legacy networking, but we need to specify what is exactly this minimum subset that we need. We get rid of everything that we don't need, right? And essentially what they do repeatedly all the time, they discover each other, right? So these agents need to discover each other. They choose out from each other who are my friends, so who are from the same control realm, essentially. And then from these, they choose out some kind of neighbors, which we call neighbors. Neighbors are essentially routing, potential routing endpoints, right? So or whom you would route. And the control plane is now being deployed on top of that, meaning control channels, of course, but also control endpoints. So essentially, they automatically decide what is the controlling element for what and where and how and so on and so on. So they, of course, then use some kind of distributed storage. They establish it actually. They do not use it, and then they can use it, of course. So as a conclusion, essentially, we try to kind of change the world. What we see today is that both NFV and SDN, they make too much usage of the legacy networking to be really fully generic in the programmability model. We would like to go back to the fundamental question. If we are in networking, we cannot assume that there is a centralistic converged view without actually telling how we obtained that in the first place. So that is the main contradiction. So if we, however, ask ourselves, how do we obtain this view? We must think about, what is this minimum common subset of protocols and FSMs and whatever that permits us to have this view, well, in any scale, in whatever the usage later will be, and so on. So it must be extremely adaptive. That's why we propose something with the self properties. So this is somehow related to this ANIMA working group, as you know. However, there are several extensions. For example, we support this compute node specifically. I'm not sure, maybe ANIMA model supports it as well, but in the protocol, certainly the paradigm is a little bit different. So I actually have a slide on that, trying to compare ANIMA to the current work, which brings me to the end of the talk. And if you have questions, please.
Okay, so we should close because we were 5 minutes behind schedule. Thanks, Arthur. We always have the list, the SDN list, RG, the NFV-RG, the NMRG, and well, you can grab Arthur on his way up to the door. So thanks to you all. We can close, right? Or do you want to make any final comment? Thank you.
First, thanks to all the speakers and all the attendees. As Diego mentioned, we will write a report and we will solicit the speaker also to give their feedback and inputs. And we will try to post that on the mailing list, potentially submit also for the IETF journal so that you can follow up. And just a very last word. I'm aware that there is a call for paper that is exactly on the same topic of the session, so management of NFV and SDN environment. It's for the IJNM journal, and the deadline is 1st of January, so we will circulate that on the list. So I think word to the speaker and attendees that your contribution can also be extended to some papers. And we try to follow up also on coordination of this joint work between the research groups. So thanks to you all, and have a nice weekend and safe travels back. Thank you.
Don't go. Wait for. No, we all are.